Yeah, thank you for inviting me, Mark. I really appreciate it.
You're welcome.
This is a good opportunity to meet people at CU Boulder as well, since I actually haven't met any of you. So I'd like to just kind of explain what I'm doing for my thesis, and maybe somebody finds it interesting or has some feedback for me. I'd really appreciate that. So this is unfinished work that I'm doing for my PhD. If I state a theorem on the board that's not fully proven or published, I'll put work in progress. And feel free to interrupt at any point and ask questions, or if you have questions about the status of a particular theorem or where I'm at in the proof of it, just feel free to ask. So it'll be a somewhat informal talk. I just want to give you an idea of what I'm doing and some of the tools involved. Okay, so I'm going to break this talk up into 3 parts. So the first part, I just want to talk about index theory and what an index theorem is to me. And then I want to talk about Groupoid-Equivariant tools that are used to generalize the tools that are in the non-equivariant case. And then I want to talk about what an index theorem would look like in a G-equivariant case using these tools. So the first thing I'll mention is Fredholm operators, because anytime we're talking about index, we're typically talking about the Fredholm index. So a Fredholm operator is a linear operator F, typically between Banach spaces, and it's Fredholm if these kernel and co-kernel are finite dimensional. So if they're finite dimensional, we can take the difference of their dimensions, and it's a well-defined integer for this operator. I'm reluctant to say bounded because the first example I'll give you of a Fredholm operator is not a bounded operator, so I'm just going to hold off on that. Some really important facts about the Fredholm index. It's invariant under homotopies of Fredholm operators. So if you have a homotopy of Fredholm operators, the index stays constant. And if you do a compact perturbation of a Fredholm operator, it has the same index. So it's just a very robust integer that you can associate to a Fredholm operator. An index theorem is just going to be a novel way of describing, I don't have to click on anything. It's just a novel way of describing this index. Since it's such a topologically robust integer, it's usually some kind of co-homological formula or some kind of topological description for the index. Okay, so here's the primary example. If our Fredholm operators are elliptic pseudodifferential operators on a compact manifold, it's a major theorem that these operators are Fredholm. I'm not really going to explain what a pseudodifferential operator is. If you want to think of them as some kind of generalization of differential operators, that's fine. But they happen to be Fredholm, which is cool. Specifically, if we're on a closed or compact manifold, it has to be compact for it to be Fredholm. If you want to think of it in a slightly nicer setting, most people assume that their pseudodifferential operators are order 0 because they actually extend to a bounded operator on L2. So normally we take in smooth sections of a bundle, and the operator differentiates them in some way, and we get smooth sections of another bundle. But if it's order 0, it's actually just a bounded operator, and it can extend to L2 uniquely. So most people just assume order 0 for simplicity. What's special about pseudodifferential operators is they have something called a principal symbol, or at least one of the special things. You can think of it, if you're talking about differential operators, it's essentially like an algebraification of the top degree part of the differential operator. And what I mean by algebraification is, if you think of it as like coefficients times derivatives, like partial by partial x, you think of partial by partial x as like a vector, plugging in like the ith coordinate of the covector in for that, like say partial by partial x, gives you a map from the cotangent bundle to this Hom bundle. So it's basically just the coefficient. It's like a coefficient map, but just the top degree. And what it means for an operator to be elliptic is that this symbol is invertible outside the 0 section on the cotangent bundle. Which is really where the topology comes in. So if you have one of these maps, so like if you have a section of this Hom bundle, and it's an isomorphism outside the 0 section, the 0 section is a compact subset because X is a closed manifold. So we have a map between bundles that is an isomorphism outside some compact subset of Tx, which means that we have a K-theory class on T star X. I'm going to conflate Tx and T star X this whole talk, I'm really sorry, but they're the same topologically, so just forgive me. So we do get a K-theory class from this. And what the Atiyah Singer index theorem states is that the index, the Fredholm index of this pseudodifferential operator is an intersection product between the Turing class, or the Turing character of this K-theory class, and something called the Todd class of the complexified tangent bundle. If you integrate this over Tx, you get the index. So it's just basically a novel way of describing this Fredholm index that was on the other tab. If you guys want more context for this, I like to think of this index as being a very analytic piece of data. What is the kernel of like a differential operator? It's the space of solutions for the differential operator, right? So like the homogeneous solutions, like dx equals 0. That's the kernel, it's the solutions to that equation. So something being Fredholm in particular means that it's got a finite dimensional solution space, which is kind of cool. So we consider the index on the left-hand side as something analytic, and on the right-hand side it's something very topological. Again, feel free to stop me if you have questions. Don't hesitate to interrupt. Right. What am I doing next? So this is sort of a co-homological formula. I'm really working in K-homology and K-theory. So I'd like to write an expression like this, but in K-theory or K-homology. So I want to talk about KK theory because it kind of generalizes all those things. So we're going to talk about C-star algebras for a second. If you've got two possibly graded C-star algebras, I'm going to assume that they're separable throughout the whole talk because I just don't want to deal with every situation where we have to assume that. So just assume all C-star algebras are separable. KK theory is built out of these things called Fredholm modules. And a Fredholm module consists of, it's a graded right Hilbert B module. So it's very much like a Hilbert space, but the coefficients, instead of being complex numbers, are elements of the C-star algebra B. And then we have an action of A, or it's just a star homomorphism from A to the adjoinable operators on this Hilbert module. That's degree 0. In my opinion, the interesting piece of information from this, and why it's called a Fredholm module, is this operator F, which is a degree 1 map, or it's a degree 1 operator. Degree 1 roughly means F looks something like, maybe call it S or something here. It roughly looks something like this, so it's sort of off diagonal. It'll map the odd part to the even part, and the even part to the odd part. So it's a degree 1 operator, and if you forget the phi of A for a second, it's basically just saying that F squared is the identity modulo complex, and it's also self-adjoint modulo complex. And this one is just saying that it commutes with the image of this homomorphism modulo complex. So here's, maybe you can keep this in mind. If you don't want to think about the phi, if you let A be unital, these conditions are literally just saying that it's self-adjoint modulo complex and squares the identity modulo complex. A useful fact about Fredholm operators is called Atkinson's theorem. A Fredholm operator is the same thing as just an operator that's invertible modulo complex. So this first condition is roughly stating that it is a Fredholm operator whose inverse modulo complex is itself. So it's why it's called a Fredholm module. We're going to denote EAB as unitary equivalence classes of these things. I'm not going to explain what that is, but it's just, you can talk about unitary equivalence classes, and then if you mod these out by a notion of homotopy, you get KKAB. So that's the idea behind KK theory. Right. Some special cases. So if you just look at the second input, and you just put in the complex numbers for the first one, it's K theory. So if you're looking at topological space X, topological K theory is given by plugging in C0 of X. If you have a C-star algebra, then plugging in a C-star algebra in the second component is the C-star algebra K theory. And if you know about K-homology via extensions, it's the same as KK, where you plug it into the first variable, complex numbers in the second. And if you know anything about geometric K-homology, I think you might need this to be a CW complex. I'm not sure. Robin, do you know about that?
Yeah, you gotta watch the course a little bit. I mean, it's true for finite CW.
Yeah, so I think, I might have forgotten to specify that, but I think this isomorphism was proved was finite CW complex, which is pretty general. Yeah, and so Another one to look at is if you plug in C into both variables, you get the integers back. And the identification here for the integers is you take one of these Fredholm modules, and although this thing by itself actually has index 0, the top right component or the top left component might have non-trivial index, and so that's the identification, is just taking the index. So it's a really good tool for doing index theory because you can extract the index from these KK classes. Okay. The other really cool thing about KK theory, besides the fact that it generalizes a lot of these other K theories, is that there's a really interesting product. This is a sort of basic version of it. I think there's some ramped up versions that are a little bit more general, but I like this one. If you have a KKAB class and a KKBC class, you can tensor them over B to get a KKAC class. It's got a lot of really nice properties. It's associative. It generalizes a lot of familiar products from K-theory and K-homology. For example, K-theory is built out of vector bundles. So there's a product that's basically, it's a generalization of like taking tensor product between vector bundles that you can define on K-theory. And then there are K-homology products that it generalizes. And if you want a rough idea of what it is, if you take these two Fredholm modules, you take the B-balanced tensor product of those Hilbert modules, you keep the phi of A homomorphism, so it's still still has that homomorphism from A, and then the operator for this product is some way of formalizing this expression f tensor 1 plus 1 tensor f prime. So really you want to do f in the E direction and f prime in the E prime direction, but it's just, you can't just write this down. It's a lot more complicated than that. So it's actually a very, very technical construction. So I'm just going to skirt that under the rug for now. Okay, so let's talk about the index theorem in K-homology. So if you have an elliptic pseudodifferential operator, it actually forms a K-homology class on X. And the symbol, again, forms a K-theory class on Tx, or T star X. And in fact, if you look carefully at this, these vector bundles are pulled back from X to Tx. So really, this whole thing fibers over X, and we could view sigma p as being a class in here. So kk c of x, c0 to t star x. Okay, so if you notice, sorry, let me continue with this first. The t star x here is actually almost complex. You can look at the sort of vertical component and horizontal component, and you can form a Dolbeault operator for the tangent bundle or cotangent bundle. And this Dolbeault operator is elliptic, so it forms one of these. It's an elliptic differential operator, so it forms one of these K-homology classes. And what you should notice is that this C-star algebra and this C-star algebra are the same, so you can take the product of these two things, and it turns out that this product is the K-homology class of P. So it's another kind of factorization of, if you think of this as being some kind of generalized index for P, it's a factorization of that into basically something coming from the symbol of P and something coming from the manifold T star X. So I put this next to the T Singer index formula so you can kind of compare. You can actually get the original T Singer index formula from this one by using like Turing characters, really clever arguments in Poincare duality, and embeddings. So you can actually get the original one from this. There are a couple of advantages to this kind of a formula, though. For example, X doesn't actually need to be compact. If you have an elliptic pseudodifferential operator on a non-compact manifold, it's technically not Fredholm, but it still forms a K-homology class on C0 of X, comma C. So this theorem still holds, even if X is not compact, but there's no index, so you can't really pass to this. So it is a slightly more general than the original formula. Okay, one last version of the index theorem is you can represent it as a commutative triangle. I'll hopefully just explain briefly what these bits are and why it forms an index theorem. This was, I believe, introduced in a paper by Paul Baum and Douglas in, I think it was the like some operator, like it's this Kingston conference proceedings. You guys know what I'm talking about? So there's a really nice paper in there by them about this. And this here is the geometric K-homology of X. And it's basically built out of a spin C manifold on top of your space X. And it's closed, so it's compact, equipped with a vector bundle. And when I say over X, I just mean there's a map from M to X for this spin C manifold. I've moved the diagram up here. Just want to explain what these maps are. So C takes a K-theory class up here, which is a bundle homomorphism that's isomorphic outside some compact set. 2 vector bundles on Tx. And what you do to get a compact spin C manifold is you take Tx and you take, say, take some metric on Tx, and you look at like the ball bundle, and you glue the ball bundle to itself on its boundary. So now you have some sphere bundle over X. On the top hemisphere, you take E, and on the bottom hemisphere of this sphere bundle, you take F, and you glue them together with sigma. So as long as your metric is defined in such a way that sigma is an isomorphism outside maybe the half ball or something, then this construction will give you a well-defined vector bundle. So this is your manifold, this is your vector bundle, and you have a map from this sigma X to X. There's a natural map to X. So this is an MEV for the geometric K-homology. And that's what this map is doing. So the next map is twisting. So if you've got one of these MEVs, basically the mu map just takes an ME and a V, and it takes this KK class given by the vector bundle. So this is a KK C0 of X, comma C0 of M, or I guess C of M since it's compact. And you're tensoring over C of M with the Dirac operator on M. So spin C manifolds have a Dirac operator. And you're taking a product here, so it's called twisting because this generalizes twisting of Dirac operators. Okay, the last map in this triangle is the map that goes from K-theory Tx to the K-homology of X, and it basically just is a map that satisfies this relationship. So it takes the symbol of a pseudodifferential operator and maps it to the K-homology class of a pseudodifferential operator. I think this is the most interesting map out of the three, just in my opinion, because I think, if you just look at this, it doesn't really look like a way to define a map. Like, in here, is everything in here formed by the symbol of some pseudodifferential operator? The answer is yes, and you can actually define a map like this. But that's usually not how people define this map. So it's, I think it's a really interesting map. All of these three maps are isomorphisms. So it's really identifications of these different K groups. And it encodes an index theorem in the following way. So if you follow the maps, starting with the sigma p up at the top, if you follow these maps, the OP map takes sigma p to p, and then if you apply these maps to sigma p, you basically get, this is your E for the MEV. It's some vector bundle that's determined by sigma p, and you product over sigma x with the Dirac operator on sigma x. So it looks exactly like this formula-ish. I say exactly, but they're obviously very different. But here, Tx is non-compact, and sigma x is some compactification of it. So they really are very similar theorems. It's just, in this case, we're looking at some compactification of Tx, and here we're looking at just Tx. So yeah, the index theorem is encoded in this. Eventually, when I pass to the Groupoid-Equivariant case, I'm going to be dealing with a different type of geometric K-homology in that situation. And in that situation, I think this was due to Emerson and Meyer, but they actually don't require that the manifold is compact. So we'll actually get a formula exactly like this from the diagram, because we don't need compactness for that theory. Okay, I want to pass to the Groupoid case. What time is it? Great, this is perfect timing. So 20 minutes for that part. We'll talk about this for 15 minutes, and then I'll talk about index theory in the Groupoid-Equivariant case. So I just need to introduce a couple of tools to pass to the Groupoid version. We're doing an index theorem for pseudodifferential operators, so I need to define what a manifold is in the Groupoid action case, what an equivariant elliptic pseudodifferential operator looks like in that case, and since we need KK theory and K theory, I have to define, like, say, G C-star algebras and what these things look like. So I'll just go kind of briefly through these so you have an idea of what the analogous constructions are, and then I'll talk about an index theorem in this case. Any questions so far about what I've talked about? Okay. All right, so let's talk about G-manifolds. I'm going to assume that G is a proper, locally compact topological groupoid. I think I'm just always going to assume that for the remainder of this talk. Since maybe it's not universally clear what proper means, I'll just define what proper means for a groupoid, because I didn't actually define it in my slides. So a groupoid is proper if the map RS from the groupoid to its object space Z cross Z, if this is proper. Okay, so that's what I would mean by a proper groupoid. We're also going to be dealing with proper G spaces. Okay, so X is a proper locally compact Hausdorff G space with an anchor map. So a G space is proper if the action groupoid is a proper groupoid. Okay, so that's what proper means in this situation. I just didn't define it in the slides, so I figured I'd write it down. Okay, so we're going to be assuming this throughout. It's actually a pretty restrictive condition, so keep that in mind. Okay, so X, this G space is a G manifold if the fibers of the anchor map happen to be smooth manifolds. So it's really a family of smooth manifolds over the base space of the groupoid. And they need to be continuous in some sense, these smooth structures. So we make sure that the charts for the smooth structure are given in neighborhoods of X. So these charts kind of look like we've got our manifold up here. It maps down to the object space Z. And we're taking charts of the form like this, U. And then we're mapping them to maybe I'll map it down here. Sorry, I didn't practice this picture. We're mapping them to Z cross Rn. So this goes to like a let me green. This goes to like a neighborhood like this, and the smooth structure for the fibers of rho. So these are smooth manifolds here. The smooth structure is coming from restricting these charts to these fibers over R. Okay. The more important things are the change of coordinate maps are continuous, and all the rho fiber-wise derivatives of the change of coordinate maps are also continuous. Just these three conditions here is what it means for X to be a continuous family of manifolds over Z. And the last condition, that G acts via diffeomorphisms, means that it's a G manifold. Okay? So I'll actually be using the concept of continuous family of manifolds later on in the talk. So I did want to point those three conditions out as what means to be a continuous family of manifolds. I guess one other point I want to make about manifolds is, since the smooth structure is only in the fibers of this rho map, if I write down like Tx anywhere, I mean the rho fiber-wise tangent space. There's no global tangent space. It's just in the rho fibers that we have a tangent space. And these conditions mean that glues together to a nice bundle. Okay. So what is a pseudodifferential operator on one of these things? If we've got two G bundles, you can hopefully imagine what a G bundle looks like. It's a vector bundle with a G action. If you have a operator between smooth sections of two G bundles, then it's a pseudodifferential operator if it fibers as a family of pseudodifferential operators over rho. And again, we need to talk about what it means for that to be a continuous family of pseudodifferential operators. So the notion that I'm using is that the full symbols that are defining these operators in coordinate charts, these are the coordinate charts, so really they have to come from some global, or like a symbol, full symbol in this whole chart. And restricting to these fibers will give you the full symbol for the PZs. Okay, and it has to be smooth in the fiber direction and continuous across the base. So this has to be sort of suitably defined. There's a really great paper by Patterson about these operators, specifically in the context where G is a proper continuous family groupoid. Continuous family groupoid just means that the range and source maps, if you think of those as, so that it's a map from the groupoid to the object space, if it's a continuous family of manifolds over the object space via these two maps, with a little bit extra, then it's a continuous family groupoid. Okay, if you have one of these things acting on a proper cocompact G-manifold, so the quotient is compact, then this family of pseudodifferential operators actually forms a KK class. So there's a nice paper by him. I think some of these conditions can be relaxed a little bit, because this assumption here means that the groupoid itself has smooth structures in the fibers of the range and source map, but I don't think that in KK I don't see why that would be necessary. So I'd like to relax this, but I haven't proved anything in that situation. I just think it's a little unnecessary to require smooth structure for what I'm going to do here. Okay, but for the sake of the talk, I'm just going to assume continuous family groupoid for all the theorems that I'm proving, because there's already work done on making a KK class out of these. Okay, I want to talk about KK classes, so I've got to talk about G C-star algebras. I'll try to be a little brief about this. A C of Z algebra, so Z you can imagine is going to be the object space of a groupoid, but it could just be a locally compact house source space for now. It's a C-star algebra with an action of C0 of Z. So an action would look like a map from C0 of Z into the center of the multiplier algebra of A. And the condition that we need is that if you apply all of C0 of Z to A, you should get A back. Okay, I'm going to be using this notation a lot. So the fiber above a point in the base space is just the algebra modded by the functions vanishing at that point. So this is a really common trick to get fiber above a point in algebra, modded by the ideal of functions that vanish at a point. Okay, here's an example. If you've got a continuous map from X to Y, and they're both locally compact Hausdorff spaces, then C0 of X is a C0 of Y algebra via precomposition. So if you precompose by F, it's making functions on Y become functions on X. The only issue is that this map, since it essentially won't map to C0 all the time, it will map to CB. So they'll be bounded functions, not necessarily vanishing at infinity. But this is the multiplier algebra of C0 of X. So this is exactly what you would want in this situation. Okay, so we know that C0 of X in this situation could be a C0 of Y algebra. And so if you've got one of these maps and you have a C0 of Y algebra, we can pull it back to a C0 of X algebra by taking a C0 of Y balanced tensor product between A and C0 of X. So that's what I mean by pullback. If you want to pull back in algebra, you product it with C0 of X over C0 of Y. Okay, any questions so far? Nope. Okay, so what is a G C-star algebra? If we've got one of these groupoids, a continuous action of a groupoid on one of these C0 of Z algebras, A, is going to be a map from S star A to R star A. So it's taking something sort of in the source and mapping to the range. To make that formal, you can restrict to a particular groupoid element. So alpha over gamma maps A at the source of gamma to A at the range of gamma. And for it to be an action means that this has to be composable. So if you do A gamma prime, then A gamma, it should be the same as A gamma composed with gamma prime. Okay. The reason that we define it in this kind of weird way is just to make sure that it's sort of continuously defined. It's not It's not doing anything kind of weird. So if you actually ignore that it comes from one of these things, I think it's just called a G action, but if it comes from one of these things, then it's a continuous G action. And I'm only going to be interested in continuous G actions here. Okay. So this guy Legal came up with a version of KK theory that has Groupoid-Equivariants baked in. If you have two C-star algebras, assuming they could be Z mod 2Z graded if you want, a G Fredholm module is basically a Fredholm module, but where there's a G action on E. The G action on a Hilbert module is instantiated by a unitary from S star E to R star E. And I don't think I defined like what a G action on a Hilbert module is or what pullback is in that situation, but I employ you to be a little creative for the sake of time. And basically, you just have another condition here where F is essentially G-equivariant up to compact operators, is what this is saying. So we define KKG in the same sort of way. We take these unitary equivalence classes of these G Fredholm modules and mod out by homotopy. And again, homotopy is a little bit specific for KK. And in this particular example, we must take our homotopies to be equivariant the whole way through. So it has to be an equivariant Fredholm module there. Okay, so that's equivariant KK. We need to define K-theory as well. So the appropriate K-theory is actually defined via KK, which is why I did KK first. And it's just a helpful notion to go over, but if you've got a map from X to Y, F, between locally compact Hausdorff spaces, then a subset of X is Y compact if restricting the map F just to A is a proper map. So you can think of it as sort of like a family of compact sets over the base, is what Y compact would mean. As A is over Y is sort of a family of compact sets. The representable K-theory of X with Y compact support is given by Legal's KK, where you take the groupoid to be the action groupoid of G on Y, and this action groupoid has base space Y, so this is the base space of that action groupoid, and this is the equivalent of the complex numbers in this category. If you're looking at the category of C-star algebras with a G action Y action, the sort of smallest C-star algebra in that category is going to be C0Y, the object space. So you can really think of this as being K-theory of X, but equivariant with respect to this action groupoid. And it's called representable K-theory with Y compact support for very specific reasons. So Emerson and Meyer have a really nice paper on this, where they describe basically different ways of viewing this. And one of the really interesting things about this representable K-theory is that if you try to define it in terms of G bundles, like ordinary topological K-theory, you would want to define it with G bundles. If you remember how we defined K-theory before, it's two vector bundles and a homomorphism that's an isomorphism outside a compact set. The appropriate notion would be vector bundles with a homomorphism that is an isomorphism outside of a Y compact set, rather than just a compact set. If you call that VKG, what's really interesting is that there's a natural map in a KK. There's always a natural map in a KK, but it happens to not be surjective in general. So there are actually examples where there's not enough vector bundles to really generate all of this K-theory. And so this actually becomes a really interesting problem trying to do index theory here. Okay, quick example. If you've got a pseudodifferential operator that's G-equivariant, the symbol will form one of these representable K-theory classes. In fact, it forms one of these BK classes, which maps to RK. If you think about it, if Z is not compact, then X is probably not going to be compact. Okay? So the symbol is really going to be an isomorphism outside the zero section in the tangent bundle, but the zero section is not compact if X is not a compact space. So it really has to be X compactly supported. So it's an isomorphism outside the zero section, which is isomorphic to X. So it's something that's X compactly supported as a K-theory class. So that's why we need this sort of fancy version. Okay, so this is what the analog of the theorem looks like. We're going to assume that it's a continuous family groupoid, again, because that's the only situation where I'm 100% certain that the pseudodifferential operator actually forms a K-homology class. We're going to make sure that X is proper and cocompact. And in this situation, if you've got a G-equivariant family of pseudodifferential operators, then you can factor its K-homology class in the same sort of way that you did before. The difficulties are really that these groups are a little bit more complicated. So sigma p is really in this representable K-theory group, which means that it's in this KK group, and we're taking a KK product with the, again, this maybe a family of Dolbeault operators, the K-homology class formed by that. Okay, so that's the theorem that I'm working on. I've been, Kasparov actually came out with a paper pretty recently where he proved a formula like this for a case where there's a group action. And he did not assume that the group was smooth. So I think most of the time people assume that it's a Lie group action. But this theorem actually holds if it was just a group. And that's why I think some of these things about the groupoid might be able to be relaxed. But I'm still not entirely sure. Yeah. So other things is that I think the argument that Kasparov gives probably could generalize to this situation if done properly. But I've been trying to do this in a slightly different way. I think most index theorems are proved in some way or another by relying on what's called like a rotation trick. There's usually some kind of rotation that happens. When Kasparov proved his theorem kind of like this, he did a rotation in the formula for the operator itself. And what I'm trying to do is I'm trying to prove this theorem by instead looking at a rotation of Tom classes. So TTX over TX, there's really two ways to view that as a bundle over TX. Maybe you write that down. Because I just think it's kind of an interesting distinction. But the rotation type of argument that I wanted to rely on for this proof is that you can think of TTX as a bundle over TX in two different ways. So if we think of TX as a bundle over X just via pi, we'll just call it pi. There is a projection map here because it's a tangent bundle, so we'll call it pi TX. But you could also think of d pi from TTX to TX. And if you pick a connection, this can actually be given the structure of a vector bundle. It's not normally the structure of a vector bundle, but you can equip it with one. And it turns out that both of these bundles are they're K-oriented. So you can get a Tom isomorphism from the K-theory of TX to the K-theory of TTX in two different ways. And you can rotate one of these Tom classes into the other, and that rotation is the one that I wanted to use in the proof of this theorem. And there is a proof of like that, a proof of the original index theorem using this kind of a Tom rotation trick. But I think there's an issue with it, and I wanted to try to resolve that as part of this paper. So that original or non-equivariant version is in papers by Eric Van Erp and Paul Baum. So if you wanted to look at those, it's a really nice exposition. But I think there's a small gap in there that I wanted to plug up as part of this work. Any questions about this? Right. What am I doing on time?
G40. Cool.
So you might find this a little bit unsatisfactory because we have a factorization that involves a Dirac class. We typically call this kind of a theorem a reduction to Dirac because it's really just it's shoveling the index problem from a general elliptic operator to figuring out what the index of one of these things looks like. And Emerson and Meyer have like, so I've been looking through a lot of the papers. They have like 6 papers or something that are all highly related to one another. And in one of their papers about embeddings, they proved this theorem where you can actually view this Dirac class as a very topologically defined Schrick map. So you can really think of this as a sort of topological realization of something that could be considered fairly analytic. So you could, if we rely on their work here, you could reduce this to like a full index theorem rather than a reduction to Dirac kind of index theorem. So I like the statement. I think the only issue is that we might need to require an additional condition for these embeddings to work out, which is that the object space of the groupoid has to have what's called enough effective moments. Which basically just means if you take any stabilizer, so if you take any point in the object space and you look at the stabilizer of the groupoid, if you take any finite dimensional representation of that stabilizer group, it should be contained in some G bundle on Z. So if you have something like that, you can form equivariant embeddings into a bundle over Z. And using these embeddings, you can define some really topological maps here. And that's how they form that streak map. So it's a super topological kind of thing. And so if you combine these together, these are all extremely sort of topologically motivated classes. And this is just the very analytic K-homology class of P. So that's the idea behind this. Again, I put work in progress because this would rely on this other index theorem that I was referring to. Okay, I do want to talk a little bit about what the index is in this case, because it might not be clear what I mean by index. So in the non-equivariant case, if you've got a K-homology class on C of x comma C, so this can be mapped to an index in KK C comma C, basically by mapping x to a point. It's actually functorial, this map. In the G-equivariant case, we can't map to a point. The smallest thing that we can map to is C0 of Z because it's the object space of the groupoid. And so if you map the K-homology or the equivariant K-homology to the sort of the point here, this is actually isomorphic to the K-theory of the reduced C-star algebra of G. So this is really the natural receptacle for the index of an operator. Yeah, so that's sort of the idea here. Lastly, the original thing that I wanted to do with this project was actually come up with a Baum-Douglas triangle. I really wanted to know what a Baum-Douglas triangle looked like for families. And if you're looking at families, you needed a bivariant geometric theory to make the triangle make sense. And when I looked up existing bivariant geometric K-theories, the one that I found was by Emerson and Meyer in this long series of papers. And I had to understand what this whole G thing was in there, because everything was decorated with a groupoid in their papers. And by the time I understood what they were talking about with the groupoid to try to get to my smaller case, I realized that I might as well just try to do something like this for the Groupoid-Equivariant situation because like all the tools seem to be there. So this little KKG is this. It's a generalization of this geometric K-homology, but it's bivariant. If you guys want to know what this roughly looks like, I'd be happy to explain that, but I didn't put it in my slides. Up here we have the representable K-theory with X-compact support. That's where the symbols of pseudodifferential operators would live. If you map them this way and then across, you're basically going to get the symbol producted with the Dirac operator on Tx. So you get the left-hand side of that. And then again, the OP map would just take the symbol of P to P. Okay, but I think the big issue with this is how do you define an OP map if this is bigger than DK? If this isn't entirely generated by symbols of pseudodifferential operators, you can't just define an OP map to take a symbol to its operator, or the K-homology class of the operator. You have to define this in a slightly more clever way. And that's part of what I'm trying to do right now is just get a good definition for this OP map. My advisor, Eric, he's had to define OP maps in similarly weird conditions. And I think there's a sort of like a cons tangent groupoid or cons tangent groupoid approach to defining a map here, where you're sort of deforming Tx with its usual structure to something like x cross x with an appropriate way of gluing. So you're sort of connecting a symbol to the kernel of its pseudodifferential operator is the idea. But I haven't formalized that part yet. That's something that I'm working on right now. But I think a triangle like this would be cool. Again, my original motivation was to do it for families, because an index theorem that my advisor proved with Paul Baum was about these hyperelliptic operators. And in this situation, they have the symbol of these hyperelliptic operators isn't actually in the K-theory of the tangent space. It's in the K-theory of some non-commutative C-star algebra. It's a C-star algebra of a groupoid that's formed out of the more interesting tangent space structure. And what they do to prove this theorem is they actually factor the Baum-Douglas triangle for these non-commutative symbols, these hyperelliptic symbols. They actually factor it through the elliptic triangle. So I wanted an elliptic triangle so that I could try to do this problem or generalize this problem. So that was my original motivation for looking at the triangle rather than just the formula. I also wanted to mention that there are existing index theorems. So Flom, who's at CU Boulder, along with Postuma and Tang, they actually do have index formulas for proper cocompact groupoid actions. So operators that are equivariant with respect to these, they actually have like, formulas for this. It's just not very K-homological, so I think it's sufficiently different from what I'm doing. But I would love to see how they're related. I mean, it would be very interesting if these K-homology formulas and what they did are related in some nice way. So that's my talk. If you guys have any questions, let me know.
Does anybody have questions for Zach? Robert?
Yeah, just maybe on your previous slide.
Yeah.
How is the map C defined?
So C will take the KKG. Do you know what these are, Ronan? So instead of a vector bundle, it's one of these classes essentially. So you just take this class over Tx. The map to X is the projection. The map to Z is a composition of the projection with the anchor map. So the map from Tx to Z is K-oriented because Tx is a spin C manifold in a fairly canonical way. And the map to X is it's X compactly supported, right? Because it's or it's a yeah. I'll just leave it at that. Yeah. So that's why this is a lot simpler than
using the fact that Keith and Ralph define their bivariant theory using K-theory classes rather than using modules.
Yeah, I mean, they did it because this is a really, VK is a real trash theory, right? I mean, it doesn't even satisfy excision, it's like really garbage. So they just used, instead of vector bundles, they use this RK thing because, I mean, their theory is super, super pretty. I mean, it's one of the coolest things I've looked at. Because I've thought about like, what would happen if you tried to modify definitions for a lot of their constructions, and if you modify anything, it doesn't work. So it must have taken them a while to do that, but it's, I relied a lot on their stuff just to get an idea of like what stuff should be and what kind of objects to use. So I'm really grateful to their papers because they're very readable, and also I think their ideas are really interesting. So yeah, any other questions?
Any other questions for Zach? Let's thank the speaker again.
Thanks.